Welcome to the ninth lecture on graph theory. In this lecture, we will learn what is independent set in a graph and how this is related with the vertex cover of a graph, and also we will learn what is edge cover and its relation with maximum matching. So, let us start with independent set first. So, independent set. An independent set is a set of vertices such that no two vertices in S are adjacent. Okay. So, let me just give an example to explain the definition of independent set. I will consider the same example, the same graph basically. It is a bipartite graph. So, I label the vertices by A, B, C, D, E, F. Now, the independent set is a set of vertices such that no two vertices in S are adjacent, and this is a maximization problem. You have to find maximum independent set, because finding minimum independent set is a trivial problem. You just one vertex is also an independent set. So, you have to find a maximum set of vertices such that no two vertices are adjacent. And in this example, you can see that if I consider this vertex A, B, E and F, and then you can see that these four vertices are not adjacent. There is no two of them are adjacent. So, the S here is equal to A, B, E and F. Okay, so, this is a maximum independent set. Okay, so, this independent set definition is of course not only for bipartite graph. Let me give another example also. So, I will consider a 5 cycle . This is a cycle of length 5, this is called C 5. Now, here I again label them by A, B, C, D and E. So, the independent set could be here. I can take A, and then I can't take B and E because they are adjacent with A. So, I can pick either D or C. So, if I pick D, then my independent set is consist of 2 vertices, and this is the maximum independent set that you can verify, that you can't increase this size, you can't include any other vertex in the independent set, in this independent set. Now, we use these notations like alpha g is maximum size of independent set, and beta g is minimum size of vertex covered. Okay. Now, one thing to observe here, that see the complement of S here is D and C, and you can check that this S complement is in fact it is a minimum vertex cover. Whereas, for this example also you can see that here in this example S complement is equal to E, B and C, and this is also a minimum vertex cover. Okay. So, let us prove this theorem, and this is in general true, that in a graph G, S is an independent set if and only if S complement is a vertex cover. And hence alpha g plus beta g, and using the notation here, is equal to n. So, n is the number of vertices, total number of vertices in G. Okay, let us prove this one. This is an important result, that complement of vertex cover is independent set. If S is an independent set, then what we can say in terms of every edge, that every edge is incident to at most one vertex in S. So, let us look at an edge. So, this is an independent set. So, this A, B, E, F, this is an independent set. You take one vertex, sorry, one edge, and this edge is incident to one vertex from the independent set S. This edge is not incident to any vertex in the independent set. So, this implies that every edge is incident to at least one vertex in S complement. So, you look at the edges here. So, every edge is incident to. So, this form the vertex cover C and D, this is S complement is C and D. So, every edge is incident to at least one vertex in S complement. So, this vertex is incident to both C and D, which is the definition of vertex cover. So, because vertex cover says that it covers all the edges. So, every edge is incident to a vertex in S complement. So, you can write that S complement. So, S complement covers all edges and S complement is a vertex cover, right. And the other part that so if we have proved that if S is an independent set, that S complement is a vertex cover. Now, we assume that X complement is a vertex cover. X complement is a vertex cover. So, and then you have to prove that S is an independent set. Since this is a vertex cover, S complement covers all edges of G, right, because this is a vertex cover. So, it covers all the edges of G. Then there are no edges joining vertices of S, which is obvious. So, S is an independent set. Hence, every maximum independent set is complement of minimum vertex cover. So, alpha of G, which is size of maximum independent set, plus beta of G is equal to n. Okay. So, we have learned what is an independent set, and we proved that the complement of an independent set is vertex cover. Next we talk about edge cover, and we will see how edge cover is related with matching. So, edge cover and edge cover of G is a set of edges, basically a set L subset of E set of edges such that every vertex of G is incident to some edge of L. That means, every vertex is covered by the set of edges in edge cover. Let me give example again. I will consider the same example again, or so the same graph again. So, this is a bipartite graph, and these are the edges of this graph. Well, so I want to find a set of vertices, a set of edges that covers all the vertices of the graph. Let me consider these edges, for example, AD, DB, EC and FC. So, I consider my L to be these edges. For simplicity, I am just writing AD. AD means it's an edge AD. AD, BD, EC and FC. So, this is an edge cover, because you can see that every vertex is covered. So, these two vertices are covered by this edge, B and D are covered by the edge BD, C is covered by the edge, C and E are covered by this thing, this edge EC, and F is covered by the edge FC. So, this is an edge cover, and it's a minimization problem. So, this is minimum edge cover. And we know that for this graph, the maximum matching, the maximum M, the maximum matching is of size 2, and we know that this is matching, say AD and CF is one maximum matching. There could be several, but the maximum size will remain the same. The maximum matching size, the size of the maximum matching is 2. Let me consider say another graph. Again a 5 cycle. That means a cycle of length 5, and I label them by A, B, C, D, E, and for this one this could be an edge cover, but these two edges are not enough. See that D is not covered yet. So, I have to either add E D or I have to add C D. So, let me consider this edge. So, my edge cover L consists of these 3 edges A E, B C, and D C. Well, and we know that for this one the maximum matching could be say A B, maximum matching size is again 2, A D, A B and E D is a matching of maximum size 2. Now, the question is how this the size of minimum edge cover and the size of maximum matching, these two are related. So, we look at one theorem in this regard. Let me use this notation that alpha prime G is the notation for maximum size matching, and beta prime G is minimum size of edge cover. Okay, so now we will prove one theorem connecting these two sizes. Theorem: if G is a graph without isolated vertices, then alpha prime G plus beta prime G is equal to n, the number of vertices. So, n is the where n is the number of vertices in the graph. Let us see whether this this is true in our previous example. Of course, it should be. So, this is the size of maximum matching here. So, the size of maximum matching is 2 and the size of minimum edge cover is 4. So, 2 plus 4 is 6 and 6 is the number of vertices here in this graph. And here you can see that the size of maximum matching is 2 and the size of minimum edge cover is 3, and so 2 plus 3 is equal to 5. 5 is the number of vertices Well, so that is all for this part. We will prove this theorem in the next second part of lecture 9. Thank you very much.